And we're now recording. All right, thanks for joining us, everybody. This is our second RF microwave session, our third virtual symposium session. We've been doing virtual symposium sessions since this fall as a way of, reaching out to our community and providing the content that we worked hard for last spring's session symposium that obviously didn't happen for pandemic reasons. So we've been doing a virtual symposium instead. Appreciate you guys joining us. We do have some upcoming meetings to talk about briefly. Next month, March 16th, we'll be having a technical session in the evening with Anastasia Patterson of DuPont Electronics and discussing the role of material suppliers in enabling next generation sensors. And then we have a fourth symposium session coming up, but we haven't set up the date for that yet. We'll be getting that information out shortly. And all of our upcoming meetings can be found on our chapter website, imapsne.org. And there's also a link to our YouTube channel there. And these proceedings are making their way slowly but surely onto YouTube, so you can watch them again on YouTube in the future. With that said, I'd like to thank Dave Soms and Michael Johnson, who are technical co-chairs for the symposium. They've been doing a heck of a job with all the wrenches that have been thrown at them this year and just keeping it together and doing a lot of hard work. And we appreciate everything they've done. Just to reiterate, this is an all volunteer society. So, we're all doing out of the kindness of our hearts and working hard to make it as best we can. With that said, I'll pass the reins over to Dave and let him take it from here. All right, thanks, Dave. Dave, you are still muted.
Thanks, Matt. I'm not able to pull up my bar at the bottom at the moment.
All right.
Thanks, everyone, for joining. Matt, thank you. Welcome, everyone. We have had some recent events, as Matt just described, which have gone very well. Today is February 18, so we have our second RF and microwave. Oh, boy, started again. Doesn't want to let me page down. Oh, this is irritating. What causes this? There we go. In terms of logistics, we have 4 presentations this afternoon. Our first is coming to us from a distance, and it's 8 o'clock in the evening for UC, so he will be our first presenter so that he can be finished with his workday at a reasonable hour. We'll have a Q&A session to follow each presentation. There is a Zoom chat box that you can use to write a short question to the speaker. My suggestion would be to choose everyone for who you are sending to. Don't just send it to the moderator, for example. At a later date, you should receive an email that will have information about the availability of slide sets, or you can go directly to the IMAPS New England website once you have that. We expect we'll conclude today at roughly 3:30 p.m. US Eastern Time. And Matt will have, as moderator, will turn off all the participants' microphones except the presenter. Need to ask presenters to remember to put your cell phones on mute if you have them close by you. I'd like to introduce our 2 chairs for this session, RF and microwave session, part 2. Chandra Gupta from Communications and Power Industries is the chair, and Tom Terlizzi from GM Systems and Tom Green's organization, TJ Green Associates, is the co-chair. And you have their biographies here. To save time, I'm simply going to move to the first speaker, and it will be Chandra, if you will introduce the first 2 speakers. Thank you. I will stop screen sharing. Chandra, ready to go. Chandra is muted.
Tom, were you going to introduce the first 2 instead of Chandra?
Yeah, so I'm going to introduce UC and Larry is going to introduce Tom. Tom is going to introduce you, Larry. I'm sorry. Okay, so let us start. You guys can see my screen? Can you see my screen?
Oh, we cannot.
Yes.
No.
You
No.
cannot? No? Okay, hold on a minute. What is going on here?
We
How
just,
about now? Share. You can see
now
that
it's,
now?
now it's
Yeah,
starting.
now it's
Okay,
coming. Yeah.
wonderful.
Great.
Good afternoon, everyone. Our first talk will be by Dr. UC Sail. I hope I pronounced it correctly. If not, I apologize.
No worries.
Dr. Sail received his MSc, Licensed Technology, and DSc in Electrical Engineering from University of Helsinki University of Technology in Finland. Since 1997 to 2003, he was a research engineer with the Radio Lab, TKK, and since 2004, he has been with VTT. This is his present company where he is presently a senior scientist. His research interests are pretty wide, as you can see, and this millimeter wave phased array actually fits right in there. Dr. Sail holds several patents on communications, antennas, and measurement techniques, and has over 100 publications in journals and conference publications. He serves regularly on several review boards, including IEEE transactions on antennas and propagations. His title is entitled Advanced Millimeter Wave Phased Array Designs. And without further ado, I will pass this on to Dr. Sail. Dr. Sail, is yours.
Okay,
And
thank you. I'll try to.
let me stop.
You need to stop sharing. First.
Yes, I am trying to do that. Did they stop? No,
No, not yet.
not yet. Okay. Share. How do I stop this? Why is it not letting me get out of it? Stop share here. Sorry about that for a moment.
Okay. So I hope you can see the full screen now.
Looks great.
Okay, thank you. So the present topic of my presentation today is advanced millimeter wave phased array design. And here's the outline of my talk. So first, some motivation on why would we want to go to millimeter waves, and then there are some discussion on the phased array antenna basics, and then okay, it automatically went default. So then we'll discuss integration and packaging challenges, future topics, and finally we'll conclude the talk. Okay, so motivation on going to millimeter waves. First of all, directive antennas have a small physical size, and in recent years there has been a very rapid development in silicon integration technologies like CMOS and silicon germanium, which are reaching FTs way over 200 gigahertz. And also new printed circuit board technologies and materials are available, and they can be used up to 200 gigahertz also. And in millimeter waves, for example, in this now, which is coming into commercial use, so-called millimeter wave 5G systems, we can have a very wide bandwidth, like more than 400 megahertz channel width, and in beyond 5G allocations, there will be more than 2 gigahertz channel bandwidths. And here are listed some of the already allocated 5G frequency bands. This first 5G things are coming and already in use in this so-called sub 6 gigahertz band, and The other ones are listed here. The E-band is this 71 to 86 gigahertz, which is mostly used for backhaul between towers. And then these beyond 5G installations, they have not started because there are no allocations yet fixed. But first ones will be on this D-band between 140 and 160 gigahertz. They are now in consideration in ETSI association. And millimeter wave 5G radio links are typically used for last mile connection to home or office instead of mobile devices. Okay, then on the phased antenna array basics, beam steering is mandatory for millimeter wave 5G and beyond radio systems, and also for agile radar systems sharing the same frequency bands. And these integrated phased array antennas have many qualities which make them desirable, especially at millimeter waves. So we can make planar structures which are easily integrated into antenna mechanics. And these integrated phased arrays can provide agile beam pointing even with multiple simultaneous beams. And in recent years, there's been very rapid silicon component development by several IC foundries, including Anoki Wave and others. And then also we can integrate a large number of millimeter wave antennas on a printed circuit board and have efficient spatial power combining, having a large number of parallel power amplifiers. And one of the most interesting features of active arrays is in transmit mode, this equivalent isotropic radiated power increases as 20 log n. But then in a reception mode, this G over T increases only 10 to log n. We need basically bigger arrays for reception if we want to have the same let's say array gain. And then in a phased antenna arrays, usually multiple radiators are arranged in linear or grid patterns with close to half wavelength spacing. And in the phase array, each of these radiators has called a weight function, which means its feed amplitude and phase relative to others, or the other elements in the array. And the scanning range of a phased antenna array depends mainly on the the element pattern of the unit antenna, and also the antenna element separation in this antenna array grid, and also the acceptable scan loss we can tolerate, because when we scan the beam, we always lose some gain. And then some common antenna array element types include microstrip patches, slot antennas, dipole antennas, etc. And also many waveguide antennas or horns, waveguide end or horn antennas, and Vivaldi type antennas can be used. And then some non-idealities such as mutual coupling in the array, they can cause problems in scanning to some directions. Okay, and here are shown three of these basic phased antenna array types. The first one on the left is called analog beamforming, and it is the simplest method of making an phased antenna array, and it can only support one single beam at a time. And this is also this has the lowest DC power consumption of all these options. And then in the center, you can see this digital beamforming system, which has the highest number of beams or simultaneous beams can support. And this method is used mainly in lower frequencies, not in millimeter waves. And many military radars are using this kind of system, and it has very high DC power consumption, and it's deemed not to be suitable for large millimeter wave arrays. And then on the right, you can see this final one is this hybrid beamforming, which is a combination of these two other methods, and a large array can be divided into separate subarrays, and this kind of system can also support MIMO operation. And actually, this type of phased arrays are already in use for commercial millimeter wave 5G base stations. Okay, then we move on to integration challenges, or how to really make the phased array for millimeter waves. And for reasonable link distances, we need to construct very large antenna arrays, and this typically would need more than 1,000 antenna elements. And we start with low loss PCB material systems with a high layer count. Typically, they are this HDI or any layer type boards with lasered microwires. So we can really make very dense connections to the chips and the antennas. And then the wide bandwidth antenna elements are also designed on the same PCB. And we need to route quite complex feed networks and control signals between the core chips and antennas in the array, and this is a big challenge. And in order to get the best performance, co-design of the MMICs, antennas, and the integration substrate should be done. And we at VTT we have experience on
You see your voice just broke up there.
Okay, can you hear me now?
Yes.
Yeah, it's saying to me that my internet connection is unstable, but hopefully you can hear me. So
far so good.
Yeah. Okay. Good. Yeah. The modeling of the antennas, phased array antennas, is a very tedious task, and full wave EM analysis is usually not possible. So then there are some methods to accurately analyze even large size planar arrays, like using these array factor methods, and so they are not taking into account the mutual coupling between the elements, and then these so-called conformal arrays, they are very difficult to analyze and need supercomputers to really do the EM calculations. And then most of the commercial phased arrays, they are relying on let's say this telecom type phased arrays, they are relying on the repeatability of the structure or the PCB and the chips, and they are usually not calibrated, because calibration of these 1,000 elements is very difficult in real production. And on the right you can see one example of E-band TX-RX phased array, which is done here at VTT. It's the center frequency, if I remember correctly, is it's for 73 3 gigahertz, and we have 8 times 8 elements, meaning 64 elements on both the TX and the RX arrays. Okay, then we move on to these integration challenges. So it's very critical how you can package your MMICs and how to connect them to the PCB. So there are several methods on doing this, but usually they are all chip scale packages. So the solder bumps are processed directly on the mimics. And if you are doing wafer scale production, then you can also use copper pillars, because we are mostly doing prototype work or very small shared wafers. So it's very difficult for research organizations to get access to full wafers. So we have not been able to get copper pillars, but we have used this so-called laser assisted bonding, which is offered at least by this German company Pactec. So they can stack solder bumps on the dies or PCBs, and using this LAB bonding you can also adjust the height of the chip from the substrate. So this is very useful for tight phased arrays, where you want to have little coupling between the antenna and the die. And then we have this so-called antenna in package technology, and this has many uses, and usually the reduction of the antenna array, including the chip, is important. So you need to have this means that you need to have the chip very close to the antenna, and also low loss interconnects are needed inside the integration substrate. And this technology also facilitates the large scale phased arrays for 5G and 6G systems, which can be they can use the modular concept. Like we have an array of these AIP modules mounted on a carrier PCB, so we don't need to make a large scale array on as a single unit, but we can have modular units mounted on a carrier. And then you can also use these AIP models to bring millimeter wave communications to laptops, tablets, and handsets. So you can have, let's say, a stamp size AIP mounted on your handset regular PCB. Okay. And then about the thermal management, that is also very important, because millimeter waves, the per ampere efficiency is well below 20%. And if you have a large array, you can easily dissipate hundreds of watts of DC power in a very small area. And as telecom equipment vendors, they don't like to have any active cooling or even less liquid cooling in their antennas, because they are prone to failures. And then quite interesting topic is this embedded chip technology, meaning that we can we can embed the radio chip inside the PCB. So one technology step how to do this is that you have these copper pillars processed on the dies, and then you can grow copper traces to contact from the PCB to the die. And under the chip, usually you make these copper inlays, like they're usually called copper coins, or you can use thick copper layers for heat management and transfer. And for millimeter waves, you definitely need these high density interconnectors, or HDI. And we are still studying with the leading PCB manufacturers the compatibility of these embedded chips with microwires and very small pad sizes. And these embedded chips, they are currently in production for automotive radars, and they are now under intensive study for millimeter wave phased arrays, because they can really help in reducing the size of the antenna and also greatly improve the thermal performance. The other possibility which is used in currently in phased arrays is that you have the chips on the outer side of the PCB, and then you connect a heatsink on top of the chips. That is a traditional way, but this embedding of the chips, that this could be superior to the traditional way. So finally, we come to the second last slide on future topics which are studied for phased antenna arrays. So these 5G satellite connections using phased antenna arrays is also very interesting, both in satellite and ground station ends. And there's a commercial system already being deployed, this Starlink by SpaceX. And I think in the US you can already get the connection. And this I've read that they will give you quite good connections in rural areas who have no fiber or 4G or 5G connections are available. And there's a cost-driven development towards larger size core chips in CMOS and silicon germanium technologies. The currently commercially available chips are mostly these 4-channel chips, and there are some 16-channel chips already coming, and we have also designed some 16-channel chips at VTT, and this TX and RX duplexing on the same core chips is also coming now. It makes it possible that you don't need to have a separate TX and RX antenna arrays, but you can use a single antenna array and duplex. And like I already said, this antenna array size needs to be quite huge for providing an usable link distance and data rates. And these advanced thermal management concepts are very important for reliability in real deployments. And these antenna integration platforms on PCB, they are thought to be the lowest cost alternative. And this novel antenna in package solutions for integrating steerable antenna arrays into 5G mobile devices, such as laptops and tablets and handsets. They are coming also soon. And then finally, to conclude, so it's mandatory for millimeter wave 5G systems to have beam steering functionality built in and built into the antenna. Sorry, and this phased antenna arrays have entered the telecom markets now from previously only being in a military use in radar systems mostly. And low cost is the real driver for integrating silicon and antenna elements into phased arrays. And also new frequency bands are needed for 5G and beyond 5G. And we have at VTT, we have been very interested now on this D band, because there's a lot to do there, and it's in the frontier of, well, we are pushing both the PCB technology and also the silicon chip technologies together with the leading partners. And VTT has lots of experience in all parts of phased array development and testing for all frequencies, starting from sub 6 gigahertz to D band and beyond. So if you have any need for development, you are free to contact us, and we can discuss possible projects. So here are some acknowledgements. Our recent work with phased arrays has been funded mostly by these two projects, so-called DREAM project and then Luxtaring 5G. And the DREAM project is funded by European Union, and we started in last December a new continuing project called Dragon, and it will bring these D-band phased arrays closer to commercialization. And then this Luxtaring 5G is supported by Business Finland and Nokia Bell Labs. So, and there are some references included in the presentation. So if you are interested, you can take a look at those. There are some of our papers and some others. So, okay, thank you for your attention. That was the final slide.
Thank you, Jussi. That was a great presentation.
Thank you very much.
Quite a few questions come in through the chat box. I'll try to get through some of these as we can. First question is, back to that.
Sharing.
What current challenges do you find in terms of sourcing reliable materials as well as agile and matched phase shifters?
Yeah, so that's a good question. We are usually in these core chips. They are usually based on this vector modulator concept. They are not true time delay. So there's some difference if you have very wide channels. So it doesn't work so well as a TTD system.
Okay.
But what does it mean, this sourcing reliable materials? So I'm not sure I understand this question.
You see, what I've found, especially in antenna design, if you get into ceramics or other materials in the near field of a lot of your arrays, having repeatable materials from suppliers can be very challenging, because a lot of suppliers don't have good productivity data. And I'm wondering how you get around that challenge.
You're correct. You are correct. We have been working together with mainly nowadays with AT&S as a PCB supplier, and we are using this Panasonic Mectron 7N materials. Panasonic has provided test data up to more than 100 gigahertz, and we have found that they are very reliable and repeatable materials. And I've also there are other materials also, like from Isola. They have the Astra MT materials, and they have been actually used for some applications up to 1 terahertz, and they are very repeatable, and So I think this is nowadays not a huge problem.
Okay. I guess another question is, what's the largest array size that you've made? Or designed?
We have, I think our largest size is 256 at VTT, but we are now in this Dragon project. We are aiming at this a D-band for 1024 elements, and that should give a reasonable link distance of a couple of 100 meters.
Okay. I guess another question is, where do you see the cutoff between going from air cooling to liquid cooling in terms of power dissipation and thermal dissipation?
That's not really my area of expertise. We have used in small prototypes. We usually have a fan cooling the array, but in this dream project we just demonstrated a D-band radio link. It was not a very big size array, but we have a couple of watts of DC dissipation in the array, and we have a heat sink mounted on top of the chips, and then we have a fan, and there's no problems in that there. But I would say that this liquid cooling is something that it's to be avoided in telecom systems. It could be possible for, say, for military radars or so.
Correct. Okay. And I guess along that note, another question that came in was, what tends to be the typical PA peak power per antenna needed for these arrays versus frequency?
Yeah, it's usually like I said, that the one of the good things of the phased arrays is that you don't need very high power single amplifiers there, because you have this spatial power combining. So if you have 1000 small power PS, then you will get a very high output from your array.
All right.
But it depends also on the technology what you use. For, let's say, for this silicon germanium antenna, silicon germanium chips, I think the maximum is about, let's say, plus 10 dBm to plus 15 dBm at E band, and at D band it's less, like couple of dBms
Gotcha.
per PA.
Okay. I think we have time for maybe one more before we need to move on. How do you approach the issue of phase shifting registers versus true time domain delay control?
Yeah. Yeah, so like I said, we mainly use these vector modulator type phase shifters in the arrays, because these true time delay systems, I'm not very familiar with those, but I know that they are superior for if you want really wide bandwidths, simultaneous bandwidths going through the phase shifter. But it's usually it's done so that you have SPI bus controlling these core chips, and they can be done in parallel, or they can be daisy chained. So it's depending on the system, and you have usually an FPGA which holds the code books needed for having the weight functions of each antenna. And depending on how fast you want to change the beam, you can also have some memory inside the core chips. So it's faster that you just send out a beam number to your core chips, and they know what to apply to the antennas. That's the other way. The simplest way is just to bit bang all the weight functions to all your antennas at one time, and that's slow, but it's done. It can be done like that also.
Okay. Actually, we might have time for one or two more. How important is amplifier efficiency in your typical designs?
I would say that it's very important, but usually the millimeter wave power amplifier, it's not possible to get high efficiency, because it's also a matter of integrating other functions together in the same core chip. So that's why it's usually silicon based technologies like silicon germanium or CMOS. I know that some different technologies could be more efficient, but they cannot then integrate the digital functions also needed in the core chips.
Okay. Another question, is the current industry more concerned with pattern / beam agility in data throughput versus power efficiency of completed design?
Yeah, it's I would say that it's a trade-off. Because usually the only way to make big phased arrays is that you have several core chips having multiple channels, and it's high integration of stuff into the chip, and you need those kind of technologies that can provide all the functions, both digital and analog, and but of course power efficiency is important, because you can reduce the heating or loss the heating, and also you can improve your radiated power. But yeah.
Okay. Another question is Floquet analysis or eigenmode analysis useful in your design method?
I guess this means for the EM analysis methods. It's this is not my expertise. We are mainly using as commercial solvers like HFSS and so on. So.
All righty. What is the typical failure rate in your manufacturing for these full builds, and also what is the most sensitive areas to be concerned about?
Yeah, this is a good question. Because we are research organization, so we really don't manufacture in high numbers. But I can say the failure rate in prototyping is quite quite big, and it's mainly due to that we are trying to push the manufacturer, or pushing the frontier of PCB and the silicon technologies, and it's also this interconnecting or mounting the core chips on the PCBs. That is usually the biggest point of failure. So if some solder bump is not soldering properly, because we are using really small bumps, like for these D-band core chips, we have 60 micron solder balls, and they are very tricky. And also, if you have if your PCB is not perfectly flat, then you can easily get into trouble with this solder reflow problems. One of the bumps can be not connected properly, and your array doesn't work.
All right. Another question: when looking at terahertz types designs, when looking at transmission lines, typically they can become fairly lossy. Has that been overcome with longer transmission lines, or?
Yeah, these transmission lines are lossy at higher frequencies. So to get the E-band is for PCBs, it's usually around 1 dB per centimeter or 1.5 dB per centimeter, something in that range. And when you increase the frequency, you have more losses, but also the array size gets smaller with frequency, so you don't have so long transmission lines. So these big arrays, they are using these repeater amplifiers inside the array. Another possibility is to use the so-called system that you only distribute local oscillator signals and then some IF signals to the core chips and let them mix the signal to the final frequency. That's another option.
Alrighty.
Actually, for this Dragon project, we are considering to do that.
Michael, I think we need to recognize it's getting close to 2100 hours for UC. So,
Definitely. I was just going to cut it off at that point.
okay.
Thank you, UC. Great chat and definitely very informative.
Thank you
Thank
very
you
much.
very much.
It was a pleasure.
Thank you.
I think is Chandra still there, or is Tom introducing the next speaker?
Tom will introduce Larry.
Okay.
Unmute myself. Okay, our next speaker is Larry Hawkins. His presentation is entitled RF Integration, New Highly Integrated Transceiver with RF Front End, and an acronym RFFE. Larry's working at Richardson RFPD. As far as his biography, Larry's a good friend, so I'm going to be kind to him. But Larry is a director of technical marketing and integrated solutions and systems at Richardson RFPD and has over 25 years of experience in RF, microwave, and communication. He received his BA in electrical engineering from the University of Utah with the focus of RF microwave and has worked for L3 Communications at Aeroflex. He did a great job for me on some RF modules and analog devices on Mimics, and now at Richardson RFPD, with positions ranging from engineering, applications, management, and marketing. He has written and presented over 20 papers in the RF wireless industry, including at the big microwave show, the IMS show, and has a broad range of experience in the industry. All right, Larry, you can take it away.
Thank you. I thought Tom was going to make a marketing joke. I would have if I was him.
No, you've done a lot for IMAPS over the past few years, so I'm going to cut off now.
Good. Thank you, Tom. I appreciate it. I'm going to run fairly quickly through my presentation. I have a lot of slides that are associated with it, so I'm going to go through fairly quickly. Let me make some adjustments here, and I will get started. Great. My presentation today is on RF integration, but before I talk about that, I wanted to introduce you to Richardson RFPD. Let me see if I can get my slides to transition. Hold on for 1 second.
If you move your cursor, Larry, off of the black bar at the top or the bottom, that might help.
Okay, thank you. Let's see if I can.
And if you're speaking, we have lost audio.
Can you hear me now?
Yes.
Okay. Let me see if I can get transition. Okay, there we go. See if I can get.
Lost audio again.
Sorry about that. Give me just 1 more second.
Larry, we've lost you.
Okay. Can you hear me now?
Now, yes.
Okay, that's great. So Richardson RFPD is a worldwide distributor for RF and microwave components. If you're interested in getting a broad view of RF and microwave components available in the market today, please talk with one of our representatives. We cover components with frequency ranges from DC to 110 gigahertz and from high-speed converters to basically power and antennas. With that, my presentation today is regarding RF integration, specifically focusing on size, weight, and power. But to start off with, as an analogy to RF integration, you can use the VW bug. You might have those interested in just putting more stuff in a chip, those interested in making their customers' lives easier, those that want things added just for their application, those interested in more performance. You have the military versions. And then you have those that marketing got a hold of. I'll take advantage of some of those. With that, on a more serious note, Analog Devices has a line of integrated transceivers that focus on high performance in a very small size. And I'd like to focus on the ADR V9002, a newly announced part that can be used for cellular infrastructure applications, but is the first integrated transceiver focused on other applications. As you can see, ADI's high-performance integrated transceiver portfolio started with the AD9361. That is this chip right here, and its variants. And it was followed by other parts that could be used for many applications, but were more focused on cellular infrastructure. The ADR V9002 is the first high-performance integrated transceiver that can be used for cellular infrastructure application, but is focused on everything else. Some highlights include increasing the low-frequency coverage down to 30 megahertz and its focus on more narrowband modulation signals. Because it was made with 28 nanometer CMOS process, it's very low power. The ADR V9002 covers a frequency range from 30 megahertz to 6 gigahertz, which allows for its use in applications that ADI's other transceivers don't fit very well, including applications in the UHF, VHF, licensed cellular, and unlicensed ISM bands. It supports a wide range of standards, such as FM, FSK, where it has a special low power mode, DMR, P25, Tetra, and LTE. And it works for applications like military communications, avionics, LMR, and cellular infrastructure. It has 2 independent receivers, 2 independent transmitters, and 3 synthesizers. One of those is specifically for clocking. With the option to use, it also has an option to use an external synthesizer as well for higher performance applications. Now, basically what it allows it to do is it can be used for FDD, TDD, frequency scanning for open channels, and many other applications. This part uses direct conversion signal pass with without the normal issues from direct conversion systems that you'd get with using normal discrete components. With its quadrature error and DC offset correction, you can get better than 80 to 90 dBc of image rejection and better than 60 dB of LO leakage over the temperature in a narrow bandwidth. The part was designed for bandwidths of 12 kilohertz to 40 megahertz, using an internal 128 tap FIR filter. Actually, there's 2 of them there, one for I and one for Q, and interpolation filters. This combined with the state-of-the-art receiver linearity minimizes requirements for external filtering. Other differences between this part and other recent transceivers is the LVDS and CMOS digital interface, which takes the place of the JSD 204 interface, allowing you to use a less expensive FPGA or processor. The combination of high performance and low power monitoring and sleep modes allows a part to be useful for a combination of difficult to meet radio performance applications and low power or battery powered applications. A truly unique combination. Dynamic profile switching for dynamic data rates and sample rates, and synchronization allow for fully flexible software-defined radio and radar applications. To go along with the ADR V9002 eval platform, several of Richardson RFPD's partners have developed platforms that utilize the ADR V9002 and could replace the development or could reduce the development time of your project. We've also designed multiple RF front ends to interface to the ADR V9002, creating full solutions to reduce customers' risk and time to market in the design. These solutions can be used to demo concepts in order to gain contracts. It can be used, it can be modified by either a partner or else the customer itself to meet specific needs, or can be used in production themselves. NextGen RF is developing a SOM to help reduce customers' time to market. This SOM hardware architecture integrates all the common hardware elements of a software-defined radio platform. At the heart of it's the ADR V9002 and an UltraScale Plus SoC, and it was designed to try to take advantage of all the unique features of that combination. The SOM supports virtually any RF communication standard. Basically, it can do narrowband, anywhere from narrowband type modulations to wideband with up to a 40 megahertz bandwidth. The SOM makes available both transmitters and both receivers in all three integrated synthesizers, supporting a range of FDD and TDD modes. Each receiver can be switched between two 50 ohm, 30 megahertz to 6 gigahertz receive ports, allowing for optimal tuning or supporting one as an observation receive path for digital pre-distortion and transmit power monitoring. The two transmit ports support 30 megahertz to 6 gigahertz with up to 6 dBm of continuous power. The UltraScale Plus system on a chip provides the optimal baseband processing capability to complement the ADR V9002. It includes up to 4 Cortex A53 processors, 2 real-time Cortex R5 processors, and an ARAM Mali graphics processor. The 7 processing cores, coupled with programmable logic and DSP hardware slices, offer exceptional baseband processing capability. Up to 2 gigabits of LPDDR4 and 8 gigabits of eMMC provide high-speed memory access. The SOM interconnect supports several high-speed flexible interfaces to the host processor. Up to 4 high-speed serial transceiver ports can be configured to support a combination of DisplayPort, PECL, USB 3, SATA, or the standard gigabit multi-independent interface. In addition to the high-speed transceivers, gigabit Ethernet and USB 2 are supported. Up to 8 high-speed LVDS signals or 16 single-ended I/O allow for custom combinations to the programmable logic. In addition to high-speed interfaces, up to 26 I/Os can be configured as GPIO, SPI, I2C, or CAN operating at 1.8 volts, 2.5 volts, or 3.3 volts. Additional storage and an interface to boot from an SD card is also supported through the SOM interconnect. The SOM is powered by a single 5-volt supply through the SOM interconnect. All the necessary digital and analog power regulators are retained on the SOM, minimizing host requirements. In addition to the 5-volt power supply the host provides, the SOM provides reference supplies of 1.8 volts, 2.5 volts, or 3.3 volts for communication interfaces between the SOM and the host. While trying to be flexible to meet all customer requirements with the SOM, NextGen is also able to customize this for customer applications. The following models show the small form factor of the highly integrated byte pipe X9002 RF SOM. A custom RF shield provides superior RF isolation along with a heat sink for the baseband processors. The 2 transmit ports and 4 receive ports are optimally accessible either through top side UFL connectors or bottom side SMP mini connectors. The SMP mini connectors can be used with some RF adapters for board-to-board connection of the transmit and receive ports. A 120-pin high-speed digital board-to-board connector allows for communication with the host board. In order to reduce our customers' risk in development and time to market, as well as make up for any gap they may have in design experience, we've developed a 758 to 803 megahertz RF front end with 5 watts of transmit power at the antenna, meant for high crest factor type signals, and a 2.5 dB noise figure. The front end provides excellent performance, and the PA uses a Doherty configuration that helps provide 42.6% transmit chain efficiency. The design can be used for public safety, military communications, or small cell telecom applications. It can also be easily modified to anywhere between 700 megahertz to 3.8 gigahertz for other applications. This front end was designed to be used with the ADRV 9002 eval platform, the next-gen RF SOM, or any other up-down converter with DPD and AGC to provide a complete solution. Besides the DE705, Richardson RF PD and NextGen RF are developing 3 other RF front ends that cover from 1.35 to 2.7 gigahertz and 4.4 to 5 gigahertz. For the low bands, we are providing 2 reference designs. One will have approximately 1 watt output and the other a 2 watt output at the antenna. For the high band, we're providing a 2 watt output at the antenna. This is all assuming a 10 dB peak to average ratio type signal. All 3 designs will have about a 1.75 dB noise figure on the receive side. We expect excellent efficiency in the 55% PAE range and a minus 40 dBc ACPR. We expect these front ends to be used in MILCOM, satellite, mainly Inmarsat, troop scatter, non-line of sight backhaul, and 5G, but the frequency bands can be modified for other applications if you have them. From an architect point of view, we've been talking about having a separate RF front end from the rest of the system. Vantion, another one of our third parties, has gone a different route and has included the LNA on the receive side and also amplification on the transmit side of a SOM. This is V-protein, and they try to take advantage of all the unique advantages of the ADRV 9002, and they've added a zinc 7020 along with it. You can notice the very small size of this SOM. Along with that, they've also designed a 915 megahertz SOM that can be used in a WISN network. Any of these SOMs can be modified to customers' requirements. I appreciate your time. All of these things are made available to you through Richardson RFPD, and we're willing to work with you on customizations. If any of these things don't meet the spot, we can help you with that. If you have any questions, would like to find out any more information, just please let us know. I guess I will open it up for questions.
Great. Thank you, Larry. That's a great talk. Just a reminder, everyone, if you have any questions, please type them into the chat box, and I'll ask them off to Larry. I guess a question I have is in terms of a lot of high-end technology built into these modules. I guess what were some of the major assembly, any challenges in terms of these, or if you comment on any of the environmental screening the modules have seen?
You know, really with the design of the integrated transceiver, with it being so low power, the integration of it with a FPGA, it required some heat sinking, but it didn't require, honestly, a whole lot of effort. The performance of the part was as such that you don't really have to worry about much filtering on it. So you don't have to worry about out-of-band spurs. The performance is actually really excellent. It's actually the highest performance integrated transceiver on the market today. And so the combination with various FPGAs is really, really quite easy with it. The chip includes APIs, so it's not very difficult to be able to program and use. It has about everything you need in a 30 megahertz to 6 gigahertz transceiver.
Alrighty. Another question that came in: what current modules does Richardson offer in ISM bands for high power output greater than 300 watts with 0 dBm input?
Good question. So 0 dBm input ISM bands, are we talking about 2.4 gigahertz? Or are we talking about,
yeah.
say, 900 megahertz? Okay.
Yeah, 2.4 gigahertz.
So 2.4 gigahertz, 300 watts. Is that saturated power, or is that, I would assume that 300 watts is probably saturated power.
Question. I guess, Bill Wallace, you had that question? Yeah, saturated power.
Okay, that's what I thought. We have actually, some of our front ends work at 2.4 gigahertz and can be used as drivers for PAs with that amount of power. There isn't any devices on the market right now that hit 300 watt peak. There are some, actually that may not be true. There are some new parts that are from Wolfspeed on the market that might be able to do that, but most likely you'll be combining multiple PAs to be able to do that. And you could use some of our front ends as a driver for multiple PAs that would go after that to be able to get to your 300 watts. Now, one of the differences, the PAs that we're doing right now, or the front ends that we're doing right now, are meant for large peak to average signals and are designed to be able to get good efficiencies for those applications. The design may have to change a little bit to be able to be optimized for the saturated type signals, to be able to get the best efficiency out of the drivers. But that can be done. 300 watts is very difficult though, but we do have some third parties that might be able to help you with the design for that.
Okay. Another question that came in: how is this device being received in the unmanned vehicle market?
That's actually a great market for the ADRV 9002, and we have multiple customers that are interested in it for that application. With a lot of the UAV market, they worry especially about current consumption. Depending on the size of the UAV, the smaller the UAV, the more they worry about it. Some of the bigger ones, power isn't an issue. Size is always an issue with UAV, and getting that size and performance together is a great combination for that application.
Great. Let's see, any more questions coming through on the chat line? Another minute or so.
Larry, if you would stop screen sharing, that would be great.
Yep, I will do that. See if I can figure out how to do that. Give me just
All
a
set,
second.
Michael?
Yep, all set. Can move on.
Okay, and Tom, you want to introduce Bill Wallace?
Mute myself here. Okay, our next presentation is called Electromagnetic Absorber Performance and Testing, and it's presented by William Wallace of Cummings Microwave Corporation. And if you're an RF or microwave engineer, absorbers are always needed. Anyway, William is a graduate of West Virginia University with a BSE with a specialization in high power electronics and power distribution. He then attended Johns Hopkins University, where he earned an MSAE, specializing in antenna and monolithic microwave integrated circuits, MMICs. He then performed the role of a subject matter expert at the Department of Defense, the National Naval Avionics for antennas on airborne platforms. In addition, he had shared responsibility with directing measurements and developing post-processing and measurement software for the facility for antenna and radar measurements at Pawtucket River, and I guess that's in Rhode Island, and electronic warfare. While at the Naval Surface Warfare Center at Crane, Indiana, Mr. Wallace aided in developing a National Science Foundation, and that's the Industry University Research Cooperative Partnership that's funded by NSF, which is a government entity, for embedded systems, as well as a patented method for predicting breakdown of dielectrically coded airborne structures due to perception and static effects between 2015 and 2018. In cooperation with the Oak Ridge National Laboratory, he and a team of 3 others developed, built, and tested and proved a new method for close proximity electromagnetic carbonization, and has a patent pending. He currently spends his days at PPG Engineered Materials, located in Avon, Mass., where he specializes in electromagnetic absorber and anechoic chamber design, as well as RF test and measurements. Okay, Wallace, you're up next.
Thank you very much, Tom. That was a lot of acronyms that I included in that. Very well done. One correction, that is Patuxent River Naval Air Station in Maryland, where I was a civilian for quite a while.
Okay, sorry.
Hopefully you see my screen with one slide up and not my notes slide here.
Correct.
And
Yep, that is correct.
thank you. And so what I'm going to present here is kind of a bad story turned very good, you know, making lemonade out of lemons. And when we had an issue internally, and how we scope that out, and what's the realistic expectation of this kind of material, given you know, just a general manufacturing environment, as well as capabilities of measurement devices. I'll go from there, and I'll step it out a little bit. I like to do some perception management as I go through my my presentation. So, and you'll see these sections called out throughout the presentation to kind of give you where we're at. So what am I going to show you today? We've gone through the introduction. Tom did a wonderful job with that. I'm going to go shortly through a business overview. We'll spend most of our time talking about real world testing of these absorbers and why it's such an issue. We'll do a little bit of discussion on thermal limitations and capabilities of polyurethane-based carbon-loaded absorbers, and then we'll do a little bit of fun talk about just some interesting materials that I've run across and where we're going next. And then after that is generally we'll have questions. So I like to have a slide of kind of perception management of what to expect and what not to expect from this presentation. I won't go through this bullet point by bullet point, but there are a few important ones here. I'm going to hit the variances that we will see in our products due to manufacturing at these levels, as well as some of the limitations in VNAs. It's very high level. There's no block diagrams of the VNA exactly describing where some errors arise, but we'll address it, and suggestions for some future states. I move pretty quickly. If I'm talking too fast or we're flipping too fast, please raise a hand on the side here and I'll slow down. One of the things I did want to point out is this is not a rigorous undertaking of this. That has yet to be done. And when you get into it, that's it's not as easy as one might think when you start looking at just, hey, you're measuring some carbon loaded foam, right? But what I like to put in all of my presentations is kind of a bit of humor, but it's always, you know, good to know we don't have to worry. The answer to everything is already known, and as we should all know, that's 42. I can talk about where that comes in the end if that's confusing anyone online. So where am I at? I'm at PPG. It used to be Cumming Microwave. PPG's rebranded a lot of their lines for PPG Engineered Materials, which encompasses Cumming Microwave, Dexmet, Expanded Metals, and a few other companies they're rolling in to this Engineered Materials subdivision. And at Avon, Massachusetts, we have three main areas of interest that we call free space, materials, and aerospace within Avon. The free space makes and designs anechoic chambers, the pyramidal and the wedge-shaped materials, the large ones that you've all seen when you're doing measurements in those nice quiet areas. The material side produces elastomers and flat materials that you can use to increase isolation or reduce EMI effects. They're very heavily involved in passive intermodulation reduction on installations. And then we have the aerospace area that makes some coatings for the F-35 program. So I'm going to quickly step into a couple of different descriptions. So we've taken some of our material when we saw some issues in manufacturing, and we did sampling of these materials, both old and new, in permittivity. And then we took those and modeled those homogeneously, as well as kind of a worst case stack up. So this is just, you know, the general that you're seeing. Most of this was done in CST, you know, trying to cut down on the initial mesh count. We have symmetry planes and boundary value problems that were to reduce the solve time. And this is shown just to, you know, there's always error in this, and it's always nice to know how this is set up in the beginning. So we're going to look at the material permittivity, how I think it arises, and what we're seeing in the data and the outcome over large samples, both in lots and how we define a lot and how lots change over time. So our process is very simple when it's said and done. We cut lightweight foam. It's not fully reticulated for most products. It's about 1.2 pounds of foam with maybe 30 to 40 inch pores per inch. And what we do is we literally put this in a cage between, if you can see my hands, two plates, and you dunk it in a tank, and you have a controlled squeeze with, you know, program time and dwell time to impregnate that material. And then that's sent through a set of rollers with some set gaps per size. Once that's done, the material is sorted by the wet weight. It's oven dried for a given time under given ramp rates and local environments. And then again, sorted by dry weight after trimming to give you your final created lot. So why is that important? That's important because it's very interesting how this foam network uptakes this slurry and how it's squeezed out with this process and what you see in the outcome. So what you're seeing here is the permittivity, the real part and the imaginary part of various samples that we've taken from old and new materials in various areas of the pyramid. And for example, this is a 36-inch tall pyramid. Some samples were taken at 27 inches, and some samples were taken closer to the base. And we had a full tensor analysis done on the permittivity. And so I've plotted these on each side, and what you can see is clearly there's a couple of data sets that are outliers here, very highly conductive. And so whether that's, from carbon coagulation, or whether that's something happened in the manufacturing or drying of it, that was not known at the time. So we look at, and we want to look at this a bit more in depth. So we pull some of that out and we look at some of these values. Again, they're very far apart in the values. When you look at these imaginary and real parts, and then you can calculate conductivity out of that, and you find that indeed this trace that's marked as 5 and 6 here, as well as 1 and 2, is very highly conductive. And so what does that mean in the outcome of our product? Well, we'll see very soon. And then this slide just summarizes what I've said before, and this all goes to the 36-inch pyramidal. Our 36-inch pyramidal, let me step back a slide or two. I saw you did see a side shot. It's actually 4 pyramids on a 24-inch base. You're seeing the side there of 2 of the pyramids. So we've seen by this sampling that indeed we've had some issues, or at least historically we've had some issues. But what does that mean on an install? This is a single piece of material. This is a block cut out about 3 inches by 3 inches. But when you're testing these, this is a whole array. So you now have some kind of population within this wall that you're seeing a response from. And how well does a sample refer to the actual anechoic chamber response or the full buildup? That's not fully addressed in this presentation, but what is addressed is how these different samples can arise in a single material at worst case values. So you've seen some of the permittivities. We'll first look at it in completely homogeneous solutions. And what you're seeing here, this is just a quick background of what was done for these frequency ranges. It's 600 or 60 megahertz to 800 megahertz. This was solved in CST version 2020 with 90 points in the finite element method. And so just quickly moving on. Again, this is the tensor-based method. I had to clear out some of this data just due to our customers. But what you're seeing here is the colored lines are the averages of each of those tensors. And it was to show that indeed the averages were calculated correctly, but also to see the drift between each direction and then the average utilized. And so when you put this in, and you put this in a full homogeneous, you see the outlier, right? It's very, very evident that there is one that is much more reflective than the others, on par by about 5 dB. And again, we take some modeled measurements and we look at, again, modeled versus measured, sorry. And we see the outcome, again, with the highly loaded being much worse comparison, right? Which is what you'd expect. If it's more conductive, you'd see more reflection to a point, right? And we do this on multiple ones to show that indeed this holds throughout multiple samples, multiple directions within the tensor, and these one data set is the outlier. So where are we at now? So we know that, yeah, indeed, we had some issues. These have now been solved. We've implemented processes to solve them, but let's say those issues arise again. Let's say, it's manufacturing. You never know what happens. The guy that really knows it, that does it every day, he's sick that day, and his backup may not fully understand the situation. You never know what happens. So what will be worst case outcome of that? If we start mixing these formulations in a product and assuming that's our worst case bounds, what do we see? So again, this is just a summary of what was done in this method. And what was done is we took horizontal slices to make 3 different distinct domains within the structure. And then on those slices, I varied those slice heights, and then I varied the domains within the material, right? So 3 domains, 3 different materials defined by the permittivity measurements. So tracing back to real measurements. And we wanted to see what comparisons could be made. So hopefully you'll see a little animation here, trying to show the different variations, both coming up from the base and going down from the tip. and all of those different variations in between, which end up being about 760 different solves. Again, these are the materials that were swept in those solves with those different slices. Same as presented before. And this is what I like to call spaghetti plots. But using realistic data, you can see this envelope of possible performances in our product if not well controlled. And this is setting the first slice at 6 inches and then varying the other 2 slices as well as materials. And this says, well, what if I just made the whole 6 inches completely a perfect electrical conductor? How do I perform then? How does that really weight that down? Because that goes back to how we squeeze out our material and where we might see pooling, or where, in the process where things settle, and what that would mean in the end, and what the boundaries to that are. So again, you have this envelope. So now I know this envelope, I know my space of operation, and I say, well, what if I start setting these different heights? And I just keep this to 3 materials. I keep the base at a very highly conductive material, and above that, a better matched material, let's say, to free space. So what do I see? Well, what I see is that it all binds up, and it's driven mainly by that highly conductive material at the base. That the material above it, regardless of how you change that cut, regardless of how you change it, lines up pretty well. It's all based on how well that's doped on the back side and your performance thereof. So in these runs, and you can see all of these run values here, what I wanted to see is, could I start placing metal in a piece? Was our product at one point so bad? And all of these were failures. Don't get the things wrong. We did not send out this bad product. But when we had these failures, what was going on and how bad was it? And what you found, or what I found, is that on some of these runs, for example, on these where this tip was about 2 inches, I could replace that tip with a perfect electrical conductor and get comparable performance to some of what was likely created. And when comparing these 2 measurements, indeed, we did see some of that when you pulled known bad material. And again, why would a manufacturer do this? Well, when you're running in these situations, you never know what happens. And if you don't have good traceability, and even with the best traceability, it all goes back down to the operators and how adamant and how detailed they are in their notes, and how quickly you can pull that out and compare it to your current data. So making this matchup to correlate to that and then pull out what that means to our process and thereby optimize the process was very important to us. And so as we did this some more, and this is just some interesting outcome of this, let's say I did other variations. What do I see? Do I start to see banding of material, and what does this mean? Well, indeed, you do start to see banding of material. I set this base at 6 inches. I set this tip at 9 inches, and I sweep through the materials on these 3 domains. And what does this mean? Well, this means I can get some very bad material if I have highly conductive material again in the pyramids. And this, to any RF guy, I think makes sense. You're looking at a 3D transition to free space, just like a 3D. I don't want to say a stub, a 2D match, right? A planar match on a network. And it's doing the same thing here, thus the pyramidal shape. And you would want a transition from the 377 ohms of free space down into your nice, highly conductive backplane. And you're breaking up that wave as you're seeing it. And again, this would be worst case, and more likely you would see pyramidal variation along the midline due to how it's squeezed and pressed out. That's a future work that's much more in depth than 760 runs, and we'll have to decide how to change that solution that is not included in this. But again, what you can see is the only item in this plot that had PEC in it at all was this, was this blue trace right here, this 571 at the bottom. And that was 6 inches PEC on the back. The rest of this, I can get much worse performing and have real material in it. It's to the stack up and how well you pay attention to your material and how well your processes are controlled and the outcome. And this is another example of, well, what if I set that at 12-inch base? What is my operational envelope then? And what can I expect to see the outcome of that variation? And so, you know, in the end, what did we really do? We did a lot of solves. We did a lot of variations. We made possible envelopes that we could see given situations if they were uncontrolled. And so that would correlate to data that we then see in the future if our process starts to drift. So that was all fun and good. That led to a lot of product process improvements that are implemented, and we now have much better control to the point that we are now seeing most of our variability is in the tester handling of the material versus the material variability itself at the moment. That's still being tracked down in the larger effort of this. But we've made a very large internal effort to really narrow down and optimize our product as we've upgraded our facilities. And so let's talk about facilities upgrading. High power testing. This is high power. I've done a lot of high power in my other lives. The CPEC that was mentioned was about 4 kilowatts pumped into a very narrow cavity, and we had levels well into the megawatts in certain areas, you know, per centimeter squared. That was a highly focused area trying to heat up a very, very thin material. So we have this product power density and thermal behavior. What does this mean? If I want that, I'd buy silicon carbide or some ceramic, and I probably wouldn't be buying polyurethane absorber. Well, that gets heavy, that gets expensive. There's challenges to installing that. So we typically state for a medium power product, 2.5 watts per square inch of operation. We test this in a small chamber. We ensure by probing that is indeed at the tip of the pyramid, and we do dwell times for about an hour with monitors at 3 inches, 6 inches, and 12 inches from the pyramidal tip. By accident, we have run excess of 6 watts per inch squared. We did not burn the chamber down, and the material survived, but it did exceed values of 200 C internally. I was actually pretty impressed. I didn't expect 6 watts to survive per square inch on that. What I'm trying to present here, it doesn't look like it's animating. This is what you would see at different back up, sorry here. This is as a plane, got some lag, sorry. As a plane wave normally is incident on these absorbers at different frequencies, oh, there the animation goes, you can see how the modes form at your different wavelengths. And this is just meant to show, I was unable for this presentation to get in some thermal imagery that we do have, but what you'll see is the thermal imagery relates to this mode setup as well as skin depth of your material and thermal conductivity of the final product. So for example, at 1 gigahertz, and you'll see later how high that rises, the temperature, the thermal radiation inside tends to center around the meat of the pyramid. When you go up in frequency, that moves to the tips and valleys, and the center volume is not so hot. And so why does that happen? You heat up the surface area. You don't heat the internal first. No, you heat the surface area. You have high thermal conductivity that travels to the volume, and as you tend to bombard that, your thermal conductivity overtakes the thermal profile within the material. So what does that lead to in thermal profiles? On the x-axis here, you are seeing seconds, and you are seeing at the beginning 25 or thereabouts degrees C, and we are turning this on, running for about an hour or steady state, and then turning it off and watching the cool down of the material. A, B, and C represent 3 inches, 6 inches, and 12 inches from the pyramid to the center line of the pyramid, tip of the pyramid, buried into center line. And so you see as the temperature, and please note the difference of these axes, these are not the same. As the temperature rises, how hot you get. So 18 gigahertz is the highest frequency we ran this at. 35 degrees C, not a big deal. 40 degrees C, not a big deal. This is after an hour of full bombardment of 2.5 watts or greater. But what happens at 500 megahertz or 1 gigahertz? 1 gigahertz, because this is SFC 18, medium power. It's 18 inches in height, dielectric constant about 1.9. So you're getting on the order of 2 wavelengths in good absorption, right? So now we look at, over time, the temperature rise. Well, 500 megahertz starts to get 55 degrees C. We hit 1 gigahertz. We're at almost 140 C. Breakdown of polyurethane, untreated polyurethane, stated at about, sorry, I've had notes here, 150 C, full breakdown. And we're approaching this. So does that mean our material is fully breakdown? Does that mean we're exploding into flames? No, it doesn't. So our material contains a latex type binder, a carbon dispersion, and then some fire retardants. Right now our fire retardants are hygroscopic. We are developing some non-hygroscopic materials, hygroscopic being tending to uptake of water. So does this mean we're destroying our material? Well, you've doped this polyurethane structure now with a highly thermal conductive solution. So while I do not currently have a full breakdown, and this is something in the future I think we will achieve for our material, I do not believe that breakdown, by testing of the material afterwards, of test and watching this over time as we cycle it, I do not believe that leads to polyurethane breakdown, as I do think the polyurethane lattice does not experience that full temperature. I think it's sheeted a little bit by the carbon solution and the thermal pathway that creates. That's my thought process. I have not yet proven that. That's up and coming. So, we've done a quick overview now of some issues we've had, how we've resolved it, how we've improved and optimized our material, some side measurements of high power thermal conductivity type measurements and how they perform within our material. And now I'm going to go more into some esoteric stuff. Previous lives, I did a lot of research, especially when I was with the DoD. I won a lot of Naval Innovative research grants while there, which is available to the civilians. And we did a lot of material research. And one of the materials that I was very enamored with was electrorestrictive materials. And these materials were investigated by DARPA in 2008. They're used in Talon currently, and in fact, there was, a famous leak of this material and this information. If you go back and look at information leaks from the Department of Defense, and if you're into that kind of history, and what you find when you look at these tend to be different titanates and strontium titanates and barium titanates with other impurities put in there. And essentially, when a wave hits it, it's almost the opposite of a piezoelectric. The wave induces a phonon within the lattice, and it shifts the physical lattice of the device. Well, that slows down the response of that device, and you can shrink some elements built on top of that. But you can also bias these. And so thereby you can tune those areas that it reacts in. And so the question I have here is, we are now looking at these materials. We know these exist. We know metamaterials exist. We're now looking at Dirac cone structures and composite graphene structures on a very high level, basic research area right now. What does that mean to tunable area effect absorbers, and where can we go with that? Well, I think, and this is personally just an opinion in the outlook on the market, this is not an in-depth research on the market, but I do think there is a highly innovative area, available for tunable, quickly tunable materials that can provide notch filtering or notch isolation in free space, in real spatial constraints. Now, let's take that one step further. If we can embed that in, say, thermoset devices in 3D printing or centering type 3D printing, and vary this with this 3D or additive manufacturing. You know, I would have said 2 to 3 years ago, additive manufacturing is nice, but I don't think we're going to see it on the industry floor. I think I've been proven wrong on that with some of the high scale and large scale 3D printing that's ongoing now. And I think as we move into the future, we will start seeing the meshing of these materials in a much more planned and structured way, to where we are fully controlling how the wave interacts with these materials and the biases thereof. And I'll leave you with those thoughts. I do have some backup slides if we have questions. I can show you some of our products, or at least I can talk to those if you're interested in what we make and the typical performances thereof. Thank you all for your attention. I am William Wallace, and I hope this has been somewhat entertaining.
Great. Thank you, William. Great talk. A couple of questions came through. I think early on in the presentation, you talked about, replacing, say, one of the tips on the cones or whatever with a perfect electrical conductor. Can you explain more what that perfect electrical conductor is?
Yeah, so in modeling, in computational electromagnetic modeling, you can use what's called a perfect electric conductor. And at a perfect electrical conductor, your E field terminates to exist. You know, it's perfect boundary, and there's no loss. So for example, if I were to model a high power device, and I were to use, say, a perfect electrical conductor versus a realistic aluminum material, you would miss the loss in that aluminum material. And if you did not include that, if your device is high power enough and your transmission line is long enough, you may start to melt that material. That loss is real. It all depends on, your use and your, I'll say, pull rate of your power. Does that answer the question?
I believe so. I guess another question I have is, if you're analyzing an array of the peaks or whatever, how do you know if a certain one is, different, malfunction, that type of thing? Is it a visual or, or when you're testing new material, how many samples do you run to qualify it to know it's good across the lot?
That is an excellent question. And that has been a lot of heartache over the past year for myself. So the answer to that is based upon your test measurement setup. That's based upon your antenna patterns and your efficiencies of those antennas. That's based upon whether you want to use amplifiers in your measurement device, and then if you do a calibration with that, do you need a pad, and do you remove that pad, and what kind of error does that add back in? So right now on our we separate our bands for typical NARDA standard gain horns. So we have a 2 to 4 gigahertz band, where really the 2 to 2.2 is inefficient, so that data is erroneous. So we really are measuring 2.2 to 4. And to encompass that, and when you look at it in time domain so that your response is clean enough, you're required to use a population of 4 different pieces. Our pieces are 24 inch by 24 inch. So you now have 4 feet on each side. The lower frequency you go, the broader your beam width, the larger your test area you need, and that defines a larger population of tests. And so if I have a piece that's driving failure in that test, because it is a contour as you illuminate that, it's not a nice flat front on that unless you develop antennas for that, which, by the way, Compass Technology Group is developing those type of antennas for the Air Force and the Navy. And we have utilized those as third-party tests. Then you have to look at what drives that result. A very laborious way of solving that is you do a full method where you move each piece into every position and every orientation, and then you look at that, you follow those throughout, and then you can assess exactly where the drivers were, especially as you look in your time domain. To address that exact issue, we are looking at creating and designing internally extremely broadband, extremely directive arrays to bring that down to a single piece. Because there's always the question, even if a single piece fails, if I have 500 on a wall, will I even see it? And that depends on your measurement system.
Gotcha. Okay, I think we have time for one more question. What is an example of a highly conductive backplate material?
So when I'll use this to answer. We have a sister company called Cumming Lehman Chambers. It's also owned by PPG that takes our material and they do the installs. They also create the shielded enclosures. Braden is another company that does this. NSI is another company that installs a lot of the measurement systems, and they have at their beck and call Vince Rodriguez, who controls a lot of the IEEE standards for these measurement results and chamber designs. He's well known in that field, and in fact, he's just published a new book. But to answer your question, you can buy shielded panels, and these are essentially plywood panels that have shielding glued to each side, be it galvanized steel or aluminum, based on how you want to build it. And as you build the chamber, these panels go together, and you use different methods to combine those together, such as flat and hat. You kind of is a method where there's kind of a T, and you bind them together as you put these deals together to get a nice reflective surface to bind your absorber onto. Does that answer the question?
I think so. Great. That was all the questions that came through on the chat. Thank you, William. Great talk. Very informative. Thank you so much.
Thank you all for your time and for this opportunity.
Bill, thank you. Would you stop screen sharing, please? Thank you. Tom, are you with us?
Yes, I'm here. Can you hear me?
I'm here too.
Oh, okay.
Okay.
I'll pass the baton to you,
Okay, sounds great.
Dr. Gupta. Okay.
And thanks for your help, Tom.
Oh, no.
Appreciate it.
Anytime, you did a lot of work on pulling this one through. Thanks again.
Okay, so this is our last paper in this session, entitled Thermal Considerations for High Power Gallium Nitride RF Amplifiers. This will be given by Manuel Romero from Wolfspeed, which is part of Cree Corporation from Durham, North Carolina. Manuel Romero received his BASC and MASC in electrical engineering, both from University of Toronto. He's currently part of Cree technical sales team, in which he supports customers with implementation of gallium nitride on silicon carbide technology across many RF applications. Manuel has over 13 years of experience in the high power RF industry. Prior to joining Cree, he worked at MACOM, NXP Semiconductors, and Freescale Semiconductors, and across several high power transistor technologies. Most recently at MACOM, Manuel led a product development and application team focused on gallium nitride and silicon transistors for RF technology market. As you can see, he has a lot of experience in this area. And without further ado, I'm going to pass this on to Manuel for his great talk.
Thank you, Chandra. Thank you, everyone. Let me share my screen here. Let me know when you can see it.
Yeah, we can see it.
All right. All right, I'm just going to see the presentation mode. Okay. Well, thank you for the opportunity to present today. As Chandra mentioned, effectively a fields applications engineer supporting RF high power transistors. And today I will be talking to you about, it's automatically moving, the thermal consideration for high power devices. The overview of the presentation is as follows. I'll go through a brief introduction of the thermal aspects of it and how that's related to reliability. I'll then show you through a graph how these two are related, pretty straightforward. Then I'll discuss the junction temperature of gallium nitride HEMTs and why that's important in reliability. I'll compare junction to surface temperature and how they differ, how they're used in characterization of these devices. I'll compare the substrates as well, because gallium nitride can be grown on several different substrates. I have two there just for comparison, pros and cons of each. I'll discuss thermal resistance and how it applies to high power transistors. Then some mounting considerations for these high power devices. And lastly, sort of put it all together in an example, where we go through the calculations. So solid state based amplifiers are often required to have very long lifetimes. For base station applications and military radars, it's easily over 10 years. These are using more and more gallium nitride RF devices due to the intrinsic performance benefits of this technology, which include the high power density, the high efficiency, and the high operating frequencies. And the reliability of these amplifiers, which are based on GaN, are primarily driven by the peak temperatures within the semiconductor. So in order to maximize the lifetime of these devices, it's very important to understand, how they translate back to the reliability of the device through the temperature and the thermal management of it. So, an industry standard way to measure the reliability of semiconductor devices is through the mean time to failure curve. And here on the right-hand side is a simple sort of a graphic of what an MTTF plot might look like. On the x-axis, you have the MTTF in hours, or the mean time to failure in hours. On the y-axis, you have the junction temperature. And an industry standard benchmark tends to be around 200 degrees Celsius, to get about 1 e to the 6 hours of MTTF. These plots are typically generated by stressing the gallium nitride devices or other devices, such as LDMOS, just high power devices, at very high operating temperatures. In the case of the devices here are created at around 400 degrees Celsius. To cause them to fail, within 1,000 hours. And then a high temperature data is then extrapolated down in time, to give you an estimate of the MTTF. And the main reason I'm showing this is just to highlight that for these high power semiconductor devices, peak junction temperature is directly related inversely to the MTTF. So if you're operating at going ahead on me. If you're operating at higher temperatures, you're going to have lower MTTF, and if you're operating at lower temperatures, you're going to have longer life. So what is the junction temperature, right? So the peak temperature is best understood maybe just by looking at the graphic here on the left, where I've basically taken a cross section of what a typical stack up of a GaN transistor on a system might look like. From the bottom up, we have the customer heatsink at the bottom, which could be aluminum, it could be copper, it could be many different items there. Above the heatsink, we have the transistor or the flange in which our GaN is attached. So this would be the flange. And on top of the flange, you'll have the GaN die. And the interface between the GaN die and the package flange is typically interfaced by a specific die attach layer, which is both thermally and electrically conductive. So this is your typical stack up. And within this stack up, sort of zooming into the GaN side of things, the peak junction temperature tends to occur in the region where the electrons are flowing across the channel. And that happens between the drain terminal, which is here, across the gate terminal, which is here, to the source terminal. So the current is flowing in this direction. And the peak fields, electric fields, tend to happen in this region, and they correlate to the highest temperature region as well. So this is sort of what we mean by the peak junction temperature as it relates to our GaN devices. And in general, this temperature cannot be measured directly using an infrared or IR system, primarily due to the fact that it's obstructed by metal layers. But secondly, because the aspect ratio of the critical dimensions here tends to be larger than the resolution of the IR systems, depending on the magnification lens you're using. So the way we go about taking surface data or infrared data in de-embedding down to the junction is effectively using thermal modeling using the finite element method. And then what we do is we take IR measured data in a statistical approach, develop a thermal model which is correlated at the IR plane, and use that to de-embed down to the junction. So how do we simulate the junction temperature, right? So because initially we have to develop a model that's correlated to measure data, the initial model is built up in a similar fashion to what we measure in the lab. So in the lab, when we're measuring the surface temperature of the die, we have the die which is packaged and sitting on a flange, or sorry, a package, which is a heat spreader. And that heat spreader or flange is mounted to a base plate effectively, which is just for larger mechanical support. This flange is then held at a constant temperature during testing. And then we have, which is controllable, of course, and then we have a hole that allows us to insert a thermocouple to touch the back of the flange. And then, so we're in real time measuring the peak temperature through the IR system and then the backside temperature of the package. And using these two numbers, we can back correlate to our measurement, to our model. And of course, in the modeling world, we do the best that we can to minimize the computational requirements by using symmetry planes, cutting it typically in a quarter of the problem to be able to simulate more effectively. So now that we sort of have that, we go about that and develop a model that's correlated to the IR data, and we use that to de-embed down to the junction, as I mentioned. The IR measurements perform effectively a spatial resolution, and the spot size of that area of averaging is dependent on the magnification. So for a 5x magnification lens, the resolution or the spot size is about 7 microns. And again, when we're doing that correlation of measured to model, on the modeling side, we also do a spatial averaging to make sure we're comparing apples to apples. But once we have the model, and here I'm showing sort of a cross-section of a simulated thermal finite element cross-section of our die, we can appreciate, I guess, the difference between what you would measure by an IR system and the actual numbers you get by de-embedding down to the junction, right? So for this particular example, a 7 micron spatial average size temperature would be about 165, and this is what we would call your surface temperature or an IR measured number. And the peak junction temperature is effectively about 40 degrees higher, and that's sort of the sweat spot here near the gate terminal of the device. And given that you have such a large temperature difference between what you measure at the surface and what's happening inside, is the reason why all our reliability reports and all our data sheets and everything goes back down to the area where the highest temperature and fields are occurring, which tends to be the region where if you operate too highly, you're going to have reliability problems, right? So we come back down to the important spot effectively. So that's sort of surface versus junction temperature, and of course that delta difference can depend heavily on the substrate that you're operating as well, right? Different substrates have different thermal properties. So here, just to drive that point, I'm comparing two different substrates, GaN and silicon carbide, right? Silicon carbide being the substrate in this case, and GaN on silicon. Here, silicon being your substrate for the GaN epi. The two materials, of course, have pros and cons. Silicon's been manufactured for a lot longer, so from a manufacturability and wafer size, it's a lot more readily available. The carbide is fairly newer, but the thermal conductivity of it is much, much higher, right? So just comparing thermal conductivities, carbide to silicon, it's about 3.6 times as high, right? With a degradation over temperature as well that's slower than that of silicon. So just to highlight the difference in substrate and how it applies to high power transistors, if we take a similar mechanical models, but just change the substrate and dissipate the same amount of power, about 60 watts dissipated evenly across the active area of your gallium nitride HEMT, you'll note that for similar temperature scales, the silicon is running a lot hotter than the carbide, of course, and that leads to a temperature difference, which translates to lifetime as well. So thermal resistance, what is thermal resistance, right? So in developing or allowing designers to translate operating conditions up to junction temperatures and therefore reliability and lifetime, we provide a thermal resistance number in the data sheets. And you can find this across all high power devices. It's not just GaN, it's LDMOS, many different devices, right? And in the case of ours, it allows you to sort of de-embed from the back of the package all the way to the junction temperature, right? So what is the thermal resistance? So the thermal resistance is effectively calculated by taking a temperature difference between two surfaces in space that support a fixed heat flow. So that would be a delta T, temperature delta, divided by the heat flow Q, and that's your thermal resistance, right? And in the case of high power transistors, typically the delta T, one of the planes is the bottom of the package that mates with the customer heatsink, and the other plane is the highest point in the temperature profile, and Q is the dissipated power. So how is this extracted? The thermal resistance, or R theta JC, is extracted via finite element simulations, similar to how I discussed previously. But in this case, we just work with the packaged device and we hold the bottom side of the flange at a fixed temperature, called that T sub C, that's fixed, it's a boundary condition. Then we dissipate a fixed amount of power. In this case, we call it P-dis, or P dissipated, within the GaN HEMT. Then we let the finite element solver calculate the junction temperature based on these boundary conditions and excitations. And then from there, we extract the peak junction temperature. And then using the T sub J, which is the junction, and the case temperature, which was a boundary condition, we calculate our delta T, right? And then we divide that by the dissipated power, and that gives you your thermal resistance, or R theta JC. That particular example was for a steady state, or sort of a CW condition where you're always dissipating the same amount of power. Of course, depending on the application, you might have modulated signals that, over time, you're dissipating different amount of powers. So to highlight, how this thermal resistance can vary, depending on modulation, I'm showing this graph here. In this plot here, on the y-axis, there's the thermal resistance, RTH. On the x-axis, I have pulse length in seconds, and there's 3 different graphs. And these corresponds to pulsed RF modulated waveforms for radar applications. You might have the green one here, which is a 50% duty cycle, pulsed down to the red, which is a 10% duty cycle. So for the 50%, you'd have the RF excitation on 50% of the time and 50% off. And for the bottom one, you'd have the RF signal turned on for 10% of the time, and 90% would be off. And what I want to highlight here is that dependent on the pulse length, for example, the shorter the pulse length, the less power you have dissipated over time. Therefore, the lower the junction temperature versus time, and therefore the thermal resistance is lower. And versus duty cycle, as you increase duty cycle, you're effectively dissipating more power over time. Therefore, the junction has more time to heat up, and therefore your effective thermal resistance is higher. And lastly, you'll note that regardless of the duty cycle, whether it's 10%, 20, or 50, all these plots converge to one single point at the top right here. And this is effectively the highlights that after a certain amount of time, in this case 1 second pulse width, the device is going to get as hot as it's going to get. regardless of your duty cycle. And this is effectively your continuous wave or steady state RTH. And I guess the point of this plot here is that depending on the application and the modulation being used at the system level, it's important to use the right thermal resistance value and be able to take the datasheet number and adjust that for your particular application. So up to now, I've been discussing everything within the high power transistor package, right? So this is, you know, everything that you would find from, you know, from us, you know, within the package. But of course, that's just part of the system, right? What sits below the device is just as important, right? Especially the interface between our transistors and the heatsink, the customer heatsink, and what's below that interface as well. And you can effectively come up with a similar approach of stacking up thermal resistances at the system level, right? You could have on RJC here, let's say, you know, resistance from ambient to junction, which would be the sum of the thermal resistance of your high power transistor, plus the thermal resistance of your interface layer, plus the thermal resistance of your heatsink, right? And the goal here of the thermal and PA design aspect of it is given a certain dissipated power, making sure that you have the right heatsink effectively and the right interface layer such that your temperature rise from ambient gives you the right reliability at the transistor level. In terms of how is the interface thermal resistance managed, this can vary depending on how you mount the transistor. So if you're, for example, soldering your device, you'll tend to have the better thermal resistance aspect of it as long as it's void free. But some customers don't like soldering because of servicing amplifiers, so they prefer maybe using interface layers such as graphite or the like. We find that indium is a fairly good interface layer because it's quite malleable. And it's sort of easy to work with. So this is what we sort of use internally and tend to recommend to customers. But if you're using this device in your with flange devices, you're screwing them down to a heatsink. You also have to be mindful of the amount of force you put on flanges, because there's also mechanical stresses over time that you also have to consider. So sort of putting it all together here in an example. I took here one of our 70-watt high-powered transistors in which we have a 500 to 3 gig demo in our data sheet that's running continuous wave. And let's say you wanted to calculate the peak junction temperature of this particular demo. What's the highest temperature you'll get effectively if you're running it at an ambient temperature of 25 degrees C. So in order to do that, if you recall back to the RTH equation, RTH is the delta T divided by the dissipated power. So we need to get the dissipated power. And from the data sheet, you can extract the typical performance of this demo over frequency. Dissipated power is effectively your total DC power plus your input power subtracted by the output power that gets delivered to your load. And we have all these numbers on the table. The DC power can be calculated from the output power divided by the efficiency of the device, right? So using these two devices, these two equations, putting them into Excel using the numbers that are listed here, we effectively can come up with this table in which the dissipated power here is in the last column. And you'll note that at 1.5 gigahertz, we have the highest dissipated power for this particular demonstration circuit, which is about 80 watts. Now that we know the maximum dissipated power, and from the data sheet, we have the RTH, which is 1.5 Celsius per watt. We can take that thermal resistance equation and solve for the junction temperature in this fashion. And subbing in the numbers that are here, you end up with a junction temperature of 145. So you can do this for any sort of application, depending on the dissipated power and products. It's sort of the same equation. So in conclusion, the reliability of high power GaN HEMS is driven by peak temperatures within base semiconductor technology. And that's true of other technologies as well. GaN on silicon, GaN on diamond, LDMOS, whatever it might be. Within Cree, we use peak junction temperatures for all reliability testing and reports. It's important to know, where your temperature references are. So depending on, what you're using, be mindful if it's surface temperature, if it's junction temperature, definitely looking for that. The peak junction temperatures are calculated within Cree using FEM simulations that are statistically correlated to measure data, again, to the embed back to the junction. The thermal resistance can be used to calculate peak junction temperatures. You'll find this in the data sheet, and based on operating conditions, you can back calculate to determine lifetime. And this thermal resistance will vary depending on modulation. So it's important to use the right value for your particular application. And there's some references here that I have, once the slides become available for further review. Thank you very much.
Thank you, Manuel. Great talk. We had a couple of questions come through. I think one of the questions you might have answered on your last slide, but mentioning, have you seen GaN on silicon versus GaN on diamond? I think you made reference to that on the conclusion side. And what's your feeling on the GaN on diamond as a realistic thermal spreader?
Well, I haven't personally worked, honestly, to support the GaN on diamond. I know that from the thermal properties of it, it's supposed to be quite superior to the carbide, and of course to silicon. But then you get into the complexities of the manufacturing part of it. How large a wafer can you support? How fragile is it? So there's always trade-offs, right? You might end up with a lot better thermal conductor, but you end up with higher cost and more difficult to manufacture, right? So I haven't myself worked directly with GaN on diamond, so I can't speak too closely about it, but there's always trade-offs depending on the substrate that you're choosing.
Okay. Next question, what would you suggest for junction temperature in pulse case, such as 20% duty cycle and pulse width?
So the erroneous plot, or this MTTF plot, will hold regardless of what modulation you're using. The key thing here, and that sometimes we forget as well, is that these plots are generated assuming steady state operation at a certain junction temperature constantly, right? So this is more for a CW application sort of condition. For pulsed application, because you're effectively dissipating the amount of power, in this case 20%, only 20% of the time, you effectively scale your lifetime by that ratio, right? So let's say if your percentage was 20%, whatever temperature you're getting, you would scale it by a factor of 5.
Okay. Another question, are low external ambient temperatures for a system enclosure for GaN devices requiring heaters within the enclosure? For example, if the unit was mounted on a pole or a mountain top.
I don't think I follow the question. Maybe if you could repeat it one more time.
Are low temperatures subject to impact device operation? We often talk about high temperatures, but what about very low temperatures?
Right. No, that's a good question. So it's not actually. What you'll end up getting is at lower temperatures, and this is true of silicon, GaN, LDMOS, whatnot. You'll tend to have lower RF losses, so you have better performances at lower temperature. But what you end up fighting is stability, because as you lower temperature, your gain, your amplification of the device goes higher. So then you end up fighting stability, making sure that you're not having too much gain, such that you end up with an oscillator instead of an amplifier.
Okay, thank you.
Yeah.
All right, another question that came through. How does the device vary for sub 6G and millimeter wave frequency for GaN? Will it be more challenging for millimeter wave to achieve a reliable GaN device?
Right. So yeah, I mean, so it's a good question, because listening to to this first speaker here, I was thinking, how does GaN apply up at millimeter wave, right? So it all comes back down to thermal handling, right? So GaN has a very high power density, right? So, some of our 50-volt technologies, the wattage per millimeter squared is fairly high, right? So when you get into the higher frequencies, your efficiencies will drop because the RF losses are higher. So you end up with, for equivalent output power, you're going to have more dissipated power at higher frequencies versus lower frequencies. So the technology, I think, would be applicable. It becomes more useful when you're trying to hit a certain peak power, multiple watts, at Ka band, for example. If you're trying to get like a 3 watt or a 20 watt amplifier in Ka, then GaN is your solution. If you're below a watt, other technologies might be more applicable.
Alrighty. That kind of concludes all the questions that came through on the chat box. Thank you, Manuel. Great talk.
Okay, you're welcome. Thank you very much for the opportunity. Appreciate it.
Definitely. Going to do a stop share and I'll pass it back to Dave, I think.
Manuel, thank you very much. That was our fourth and final presentation for today. Michael, can you hear me?
Yes, I can.
Good, okay. In terms of closing remarks, thank you everyone who has attended. This is our third of these virtual technical sessions that we've taken out of what was intended to be our annual New England Symposium last May 7, 2020. Obviously, we weren't able to hold the symposium, so we've been using the individual technical sessions every other month in these online virtual sessions. We do have a calendar for coming events. We'll get to that in a moment. I certainly appreciate the participation of our speakers, our audience. I would also like to say, since this is a volunteer organization, as are many similar organizations, I certainly appreciate very much the intense level of activity and effort put into this organizing over the course of more than a year now by Michael Johnson from Maycom Technology Solutions. Michael, it's been great working with you, and thank you.
Quite welcome.
Harvey Smith, who handles and has handled for decades all of the logistics behind the scenes for much of what happens with IMAP's New England chapter. And when we are able to hold our our symposium, which would have been the 47th year, Judy Eicher handles the much of the arrangements, contractual arrangements behind the scene. Our session chairs for this session, for both part 1 and part 2, were Chandra Gupta and Tom Terlizzi. We certainly appreciate all of the effort put into recruiting, organizing the speakers we've had. And Matt Bracey took on the challenge of trying to corral all of us strange characters and keep the organization on track as the president for this year. So those are the primary folks behind the scenes that have participated in organizing. We have another virtual chapter technical meeting coming up in March. Normally, we would have a chapter technical meeting approximately once a month from September through April, and then skip to June. With the pandemic, we're doing them virtually, and we're very pleased. We've got a speaker from DuPont Imaging and Electronics in Marlborough, Massachusetts. That will be Anastasia Patterson, and this will be her presentation, The Role of Material Suppliers in Enabling Next Generation Sensors. That will be at 5 p.m. on March 16, and you can sign on. If you receive the IMAPS New England chapter newsletter, then you will see these updates, for these upcoming events. And that concludes our session for today. Thank you, everybody. Thank you, our speakers. Thanks, everyone.
Thank you, Dave. Thanks, everybody.
Thank you.
Nice
Bye.
job, guys.
Thanks, Tom. Thanks,
you.
Chandra. Thanks, Michael.
Quite welcome.
I think we are done.